in a plane of the chalkboard here, or in the marker board, you need two numbers to write that vector. The first way, and there's two ways to do it. So there's two ways to represent a vector. And when I say this, what I'm talking about is representing a vector as numbers. That's what I'm trying to say, as numbers written down, not just, arrows, right? There are two ways to do that. The first way I'm going to write down for you, but we're actually going to save this one a little bit for later. So the first way is important. We're going to use it. Second way is going to be the way we're going to talk about mostly in this lesson. Okay? We can represent the vector F. Let's call it a force vector. We haven't even talked about forces yet, but you know it's when you push something, right? We represent the magnitude of F. So we put it in these absolute value signs, and that means that's the magnitude. That's how big it is. Is it 10 newtons? Is it 6 newtons? Is it 3.5 newtons? Whatever. So this is the magnitude, the strength, magnitude of the vector F. That's what's represented here. So it's a number, right? And you also have to specify the direction. How are you going to specify the direction of a vector? I just mentioned it to you a second ago. You represent the angle. This is what this symbol means, the angle of the vector F. Okay? This is the angle that F makes with, and this is very important, with the positive x-axis. Okay, with the positive x-axis. Now, some of you may have taken a trigonometry course before now. Some of you haven't. Some of you are just learning this stuff as you go along and picking up the trigonometry that you need from me. That's totally fine too. Although I do recommend you go take an actual trig course because you learn a lot of stuff in there, okay? But in trigonometry, you learn that when you measure angles, you always measure them from the positive x-axis. So what you do is you write down an xy plane like this. So this is x, and this is y. And if I want to represent some angle up to a vector out here, I always measure the angle with respect to this axis. It's just the accepted convention that we use. So when I say that I need to measure the angle that F makes with the positive x-axis, that's no different than trig. That's exactly what we've always done in trig. Whether or not you've taken it or not is a different story, but that's basically what it is. So if I have some vector here, let's say it's going to be a vector pointed up like this. This is vector F. So I'm going to represent it as an arrow there. This vector has associated with it two numbers. Two numbers define the length of this vector and its direction, magnitude and direction. What are those numbers? The magnitude of F is the number. That's how many newtons or whatever it is you're pushing with. That represents the length of the arrow. That's why I'm writing it along the length of the arrow. But there's also an angle that this vector makes with the x-axis, and that angle we call theta. Now, this angle in real life is going to be a number. It'll be 10 degrees, or 16 degrees, or 34 degrees, or 90 degrees, or you can even go all the way around, and we'll draw another picture in a second where it can be 120 degrees. But anyway, I hope you understand that representing this vector by these two numbers can represent any vector you want in this entire plane. If it's a short vector at this angle, then the magnitude will be smaller. It'll be 5 newtons instead of 10 newtons. If it's a really long vector, it might be 100 newtons, right? And if I want to change the direction, I just change the angle. So here it's 10 newtons, let's say here at 45 degrees, but 10 newtons at 60 degrees might be here. So by changing these two numbers, I can get an arrow representing F to point anywhere I want. Big, small, gigantic, microscopic, pointed anywhere I want, okay? So let me draw you another quick example of a vector pointed somewhere else in the plane, just so you can kind of not just look at one picture all the time. So here's xy. What if I wanted to represent a vector that was pointed way over here somewhere, like this? So I told you I'm telling you this is vector F, or it could be anything. Could be acceleration, could be velocity, could be magnetic field strength at this point, or whatever. But it's some vector, has some length and some direction. So how do I represent it? Well, I have to represent the length of the arrow. This is the magnitude of F. This is what its strength is. In terms of newtons, it's 10 newtons or whatever. In terms of velocity, it's 1.5 meters per second. It's the number associated with whatever it is you've measured. But then there's an angle that represents where the arrow is pointing, and it's always measured with respect to the x-axis. So you start from the x-axis and you go up, that's 90 degrees. That's 180 degrees, and you go past that, that's the angle here. So I'm not sure what this is. This could be 200 degrees. Pretty close to it because that's 90, That's 180. A little bit past that's probably around 200. So you have an angle. So you see what I mean? You can represent any vector. Even if you wanted to come all the way here, the angle would be measured from the x-axis all the way back here. And by specifying an angle and specifying a magnitude, I can get any arrow I want pointed anywhere. So I told you there are two ways to represent a vector. The first way requires the magnitude of the vector and the angle. If you take an algebra, you might recognize that as polar notation, right? I'm not going to get so bogged down in the terminology, but that's polar representation. That's a length with an angle. That's called polar. But anyway, that's the first way, and we are going to represent vectors that way a lot, because most of the time you're going to say, yeah, I have 15 newtons at an angle of 10 degrees. That's what the vector is. But there's another way to represent vectors. This secondary way that I'm going to show you here is very intuitive, very easy to understand, and it's really what's very most used to add vectors together, not graphically, but adding them together using numbers. And that is the second way to represent a vector, is we represent it with the x and the y components of the vector. In this case, we're talking about vector f, but I'm giving, it could be any vector that we're talking about. So we can break it into components. Let me show you what I mean by that. Let me draw the vector again. Here it is in the xy plane. X, y, like this. I'm going to draw this exact same vector f, try to do my best to represent it over here, like this. So what I have is a vector going from the origin, more or less pointed like this. That's pretty close. That's f, vector f. Now, it is true that this vector can be represented by a length and an angle. True, absolutely true. But it can be uniquely represented another way. And that other way is the following. I can represent this vector if I take the tip of this vector and draw a little dotted line down this way and a little dotted line this way. Then I can represent this vector as the following. There's a vector going this way to this point. I'm going to call that f sub x. This is also a vector called f sub x. And then the projection of this vector, if you take the tip and project it on the y-axis, then you can kind of think of this guy. I'm drawing parallel, but it's really right on top of the axis here. I don't like drawing it over there. I apologize. Let me take this away. I haven't really done anything wrong, but I just prefer to draw it over here. This guy over here, I'll draw it right here next to the dotted line so you don't erase it all. This is called f sub y. That's also a vector. Notice that this f sub x and f sub y, it has an arrow also. It's pointed this way, and this is pointed this way. So f sub x is a vector pointed only along x. It's how much of f exists in the x direction, right? And f sub y is how much of vector f exists in the vertical direction. If you think of a force that literally I'm pushing a boulder, right? I use force a lot because it's really intuitive. Everybody knows what force is. They push stuff all the time, right? If I'm pushing up and to the right, like I'm doing with F here, some of my force is a horizontal force. That's represented by this. And some of my force is an up and down, totally vertical force. And that's represented by this. The vector sum of those things, x and y components, give me the angled force that, usually is what I think I'm doing all the time. But I can think of any angled force as a sum of an x force and a y force. Now, if you look at this, I've already oriented this vector head to tail. So you can look at it. This is a vector. This is a vector. If I were to add these vectors together, I've already done it on the board. Connect the tail of this to the head of this. This is the vector sum of the x and the y component of the forces there. So because you already know how to add vectors graphically, I'm just showing you graphically that vector f is equal to vector f1 summed with vector f2. Look at it, it's right here on the board. This is connected to this, and this vector sum is this. So any force, I guess I shouldn't say f1 and f2. What I meant to say is fx and fy, okay? Any force oriented in any direction can be written as a horizontal force f sub x and a vertical force f sub y, but this concept applies to any vector. I use force because it's easy, but it's the same thing for acceleration. If I'm accelerating this way, then I can write it as an x acceleration going horizontally and a y acceleration going vertically, and I break up that angled acceleration into two different directions. Why? Because later I'm going to tell you what equations to use. that govern how things move. And it's going to be much, much easier just to write an equation that only works in the x direction for the x version of everything, and then a totally separate set of equations just for the y direction. And when I put them all together at the end, that will give me the angled motion or whatever the composite motion is. But I'm going to always do my analysis in two different directions. So breaking a vector into components is critical because you can't start any physics problem unless you know how to break things into components. So this is one example. I always draw an initial vector here because it's easy to visualize. Let's draw the other one. Notice the other vector example I gave was way across the other side of the xy plane, and it was over here. So here I have another xy plane. I'm going to draw that second vector, and I'm going to show you what the components to that one would look like. So here is x and y. And I'm going to write down the best I can. I'm not going to be exact, but I'm going to draw basically a vector that's going this direction like this. And this one I'm going to call f, obviously. What would be the x and the y components graphically drawn here? Well, what you do is you take the tip of this vector and you project it, is what you call it. It's like you're shining a flashlight this direction and you project it. Where would the shadow fall on the x-axis? Well, it would fall right about there. And then I take another flashlight and I project it this way. And now I know why I shouldn't have written that there because it gets in the way. But anyway, the projection goes over here, and this is where the shadow would fall more or less on the y-axis. So I'm going to say that this is vector f. I'm going to write my label out over here so it's a little easier to read. And what I basically said is this length here, the projection on the x-axis, is the x component. So it's going to be basically right here. This is f sub x. It's a vector quantity because it points a certain direction. And then we have a y component, which goes up here like this. And this is the y component. Now look and convince yourself again that if I take vector fx, it's head to tail with vector fy. So if I add them together, I just connect this to this, and then that gives me the answer here. So again, exactly the same thing. Vector f is the sum, the vector sum of f sub x plus f sub y. All right? So in this case, though, there's a slight difference. I mean, it's the same exact thing, but I just want to point out to you. In this case, notice this is positive x and this is positive y. So fx is positive. Let's just write it down. In this case, fx is positive because it's pointed in positive x, and fy was also positive because it was pointed along positive y. Okay? But in this case, notice that fx is pointed not this way. Fx is pointed negatively. So fx in this example was in the negative direction, and fy was pointed down. So fy was also pointed in the negative direction. So here in a couple of minutes, I'm going to actually give you an actual example where I give you a vector with an actual number, and we're going to use trigonometry to figure out what fx and fy are. I'm just pointing out that if the original vector is up here in the first quadrant here, where everything's positive, then the numbers you get for fx will be like positive 3 meters a second. This will be positive 3.5 meters a second, whatever. They'll both be positive because the vector's over here in the positive quadrant. But as you move the vector around the plane, your components can get negative. In this case, this might be negative 3.5 newtons, and this might be negative 2 newtons, because this is negative x, this is negative y. So you can have negative components of x and y, but that graphically they add up to give your original vector to you. One thing I want to point out, very important for you to understand just as a big, big picture, before we solve a quick problem actually breaking a vector down. In this representation, see, this is what we call two-dimensional space, right? We're going to sound a little bit science fiction-y here. You know, 1 dimension, 2 dimensions, 3 dimensions. It sounds really complicated. All it means is two-dimensional space is everything that happens in the plane of a board. 2 dimensions means up and down and left and right. Real life has 3 dimensions because it can come out of the board toward you. But we're not doing that now. We're doing only 2 dimensions. So for a vector that only lives in 2 dimensions, only in the board here, it takes 2 numbers to represent him. In this case, it takes the magnitude and it takes the angle. 2-dimensional space, 2 dimensions means I have to have 2 numbers to represent that vector. In this case, it was the length of the vector, magnitude, and the angle of the vector, but it was still 2 numbers. Over here, I'm representing the vector completely differently. I haven't given you an angle. I just said this vector can be written as this component and this component. These are numbers, these are vectors, but it still takes 2 of them. So two-dimensional space over here representing it this way means I need two numbers, x component and y component, to give me back my original vector. Represented this way, I still need two numbers. I need two numbers no matter what. Why? Because the vector is a two-dimensional vector. It lives in the plane of the chalkboard. So no matter how you represent it, whether it's this way, whether it's this way, I still need two numbers because it's a two-dimensional vector. What do you think is going to happen if you have a three-dimensional vector? In other words, a vector that doesn't just go up, right, left, down, but also can go towards you, so it can point anywhere in space. How many numbers do you think I'm going to need? I'm going to need three numbers. If I have x, y, and z, then I'll need an x component, a y component, and a z component to represent that vector. Three numbers for a three-dimensional vector. Or this one, I'll need a magnitude, but I'll also need two different angles. One angle from the x-axis and one angle from a different axis, like maybe the z-axis. But I'll still need two angles, so it'll be a total of three numbers. So two-dimensional vector, two numbers are needed to represent it. Three-dimensional vector, three numbers are needed to represent it. And then when you get in more advanced physics, you talk about Einstein's theory of relativity, you have four dimensions, because what is the fourth dimension? Time. And believe it or not, time is a vector too. So how many numbers do you think you're going to need to represent a vector in four-dimensional space-time? You're going to need four numbers. X, Y, Z, time. So two-dimensional vector, two numbers, three-dimensional vector, three numbers needed, four-dimensional vector like a space-time vector, four numbers needed. All right, so now we want to get back down to earth and talk about how to calculate these actual components. We're not going to do a ton of examples. We're going to do one example here, and then in the next lesson we'll do a bunch more. How do we calculate the components of this vector? Given the following, we have to pull it down to earth with real numbers so we make sure everybody understands what we're doing. Here's x. Here's the xy plane. And now instead of just telling you I have a vector f, I'm going to give you a real vector. I'm going to draw an arrow here, and I'm going to say that this distance vector, it's a distance vector. It's 10, or a displacement vector. It's a displacement vector. That's, because remember, vector displacement is a vector quantity. It's 10 meters to my mailbox. This is, for instance, my front door at the origin. This is my mailbox where I want to walk. It's 10 meters away. But I need two numbers to represent any vector in two-dimensional space. I need another number, which is the angle from the x-axis. This is 30-degree angle. So given these two numbers, I can literally tell you now, in a mailbox with my house, it's really a three-dimensional space, so it's a little more complicated. But if I draw a cartoon of my house on the board with the mailbox, I can tell you how to get there. I can say, walk 30 degrees away from this line here and walk 10 meters along that line, and you will arrive at my mailbox. Two numbers, angle and magnitude, meaning the distance. How do I convert this into finding the x and the y components, the other alternative way of representing this vector d? How do I find that? Well, you're going to end up having to use a triangle. So we're going to find the components, which we're going to call d sub x and d sub y, which is the x component here. How much of this distance exists on the x direction? How much of it exists along the purely y direction? The way we do it is with triangles, and that's why we reviewed trig. So what we have is we have a triangle here, like this. Now, inside of this triangle, we have an angle. It's 30 degrees. You just copy down exactly from what I gave you before. And we have a distance here. So this is 10 meters. So we know two things about this triangle. We know the angle the hypotenuse makes with this line, and we know the length of the hypotenuse. We know the angle, we know hypotenuse. What we want to find are what? We want to find dy, that's the distance along the y direction, the height of this guy, and dx, which is, whoops, trying to make it x, which is the length of this side of the triangle. So the vector problem boils down to a triangle problem, which is why we have to know trig for physics, because we know the hypotenuse, we know the angle. We want to know what this side of the triangle is, and we want to know what this side of the triangle is. So how do we find it? Remember we talked about sine, cosine, and tangent. Okay, let's kind of give myself a little break here to kind of have some space to work over there. Let's calculate first the dy, this length of this triangle. How do we do it? We know that sine of an angle involves the opposite side of this angle, which in this case is dy. So the sine of 30 degrees is equal to the opposite side of this guy, which is dy, over the hypotenuse, which is 10. So let's write it like this. We'll write it as opposite over hypotenuse, which is opposite of hypotenuse, which is dy over 10. So now I have everything I need to solve the equation, right? Because this is a number. Sine of 30 is a number. You can stick that in your calculator, or if you take in a trig class, we spend a lot of time in the unit circle figuring out how to calculate sine of very simple angles. So I know, because I know trig, sine of 30 is 1/2. But if you don't remember that, because if you haven't taken trig or if you've forgotten, you can go back and learn how to take sine, cosine of these basic angles, or you just stick 30 degrees in your calculator and hit the sine button and you will get 1/2 back. But anyway, we want to solve for dy. So what we do is, before I do taking any sine or cosine of anything, let me rearrange things a little bit. Let me solve for dy. D sub y is going to be equal to, multiply by 10, so it comes out here, 10 times the sine of 30 degrees. This is the form that's very, very useful because it's chopping it, for lack of a better word. I talked about that in my trig review. When you take 10, you're taking the full length of the hypotenuse and you're multiplying by sine of 30. What you're doing is you're chopping it in a sense of you're seeing how much of it exists in the y direction. You're chopping the hypotenuse to see how much of it is in the y direction. That's what the sine actually does, is it cuts it down to something less than 10, which is this dimension here, which is that direction. So we can write down that dy is equal to 10 times sine of 30, which is 1/2, so that dy is equal to 5 what? Well, this was in meters, so this has got to be a distance in meters also. So dy is 5 meters. So that means the vertical component of the distance was 5 meters. Okay. So what is going to happen along the other direction? You might snap your fingers and say, well, the other one's got to be 5 meters too, because 5 plus 5 is 10, right? But no, this is a triangle. This is not adding things in a line. This cannot be 5. If this is also 5, let's figure out what the math tells us, and then we'll use the Pythagorean theorem to prove it to you later. How do I find what dx is? Well, go back to your original definition of cosine. Cosine of 30 degrees is not the adjacent, it's the adjacent side over the hypotenuse. Adjacent is dx, hypotenuse is 10. This should be dx. Whoops, not 110, 10. But again, I want to rearrange the equation because it makes it a little bit easier to understand what's important. So I'm going to rewrite it as in terms of dx is 10 times the cosine of 30 degrees. You see how this equation has a very similar form to this one. In fact, I'm going to kind of circle this because it's very, very important that you understand. Okay, what I've done over here is I took the hypotenuse, the total length of my vector, and I multiply it by the sine. Sine, when I multiply by sine of anything, it chops the thing down to give me the vertical component. You should, in your mind, think of sine chopping it to give me the vertical side. Sine of 30 times 10 gives me that vertical side. Here, I'm taking 10, the same hypotenuse, but I'm multiplying by cosine. Cosine chops it to give me the horizontal component, the x component. So here I'm multiplying by sine, giving me the vertical component. Here I'm multiplying by cosine, giving me the horizontal component. And when I finish out the math, what ends up happening is dx is equal to 10. Now, if you go and take 30 degrees and stick it in your calculator, you're going to get, and take the cosine, 0.866. So you multiply that by 10, I don't know why I have a hard time writing dx. This should be dx here, not d giant x. It should be d sub x. D sub x, the distance in the x direction, vector, is going to be 8.66. What's the unit? Meters, because everything that we've done so far is in meters, so we stay in meters. All right? So what we have said is really, really, really important for you to understand. What we've said is that our original vector was a 10-meter distance along this angle. That is an absolutely fine way to represent the distance to my mailbox. 10 meters, 30 degrees, go ahead and walk there, you'll get to my mailbox. But an equivalent, alternative way to write that destination address down is to simply say, walk along the x direction for how long? 8.66 meters. 8.66 meters. We call that d sub x. Okay? And then walk up. Walk up a distance dy of 5 meters. And if you walk 8.66 meters in the x direction and then 5 meters in the y direction, you will get to the exact same point. Again, it took two numbers to get there because it's a two-dimensional vector. but that's basically what it is. So we've taken our vector and we've split it into how much exists along x and how much exists along y. And for now, you're just going to have to believe me that that actually makes solving physics problems easier to break everything apart. Now let's do a quick check just to make sure we've done everything right, because I want to emphasize something. Notice that this triangle is a right triangle because we've gone up, and it's always going to be a right triangle when you decompose vectors. Any right triangle means that c squared is equal to a squared plus b squared. Remember that Pythagorean theorem thing? C squared is 10. That's the hypotenuse, so 10 squared. Let's check and see if it's equal to this squared plus this squared. So 8.66 squared plus the other one was 5 squared, if I remember right, 5 meters. So let's see, 10 squared is 100, 10 times 10. Is that equal to, what is 8.66 squared? What you're going to get is 75. Depending on how many decimals, it'll be 74.99 or something, but it'll be basically 75. And then 5 squared is 25. So what you get is 100, is equal to 100. So what you have proven to yourself is that with a totally independent check, which is the Pythagorean theorem, the lengths of your triangles that you calculated were right. Because if a squared plus b squared is equal to c squared, then that means that this is a right triangle and everything exactly matches with what we should get. So this is just a check on it. And you can use that in physics to make sure and actually determine if you've gotten your answers correctly. I cannot stress how important this lesson is. If a student skips the basic concepts of vector components, then eventually you'll be solving problems where you'll have no idea what to do. I'll be pushing a block at 32 degrees, but you won't know how to break it into different parts, so you'll never be able to solve anything. And then when you get behind, you start getting that sinking feeling in your stomach because you feel like you're lost and you're going to fail. But nobody has to feel that way. You just have to know what's important and practice those things. And this is one of those things that you must practice. So we've done one problem here with the understanding the concept of vectors and what they are. Just one. But in the next few lessons, we're going to do a bunch more because I want to make sure that you get more comfortable with it so that you can find components in your sleep. And then as we go on, we'll kind of continue wrapping up our discussion of vectors, and then we'll move into motion. As soon as we get into motion, we'll be doing motion in 2 dimensions, and you'll have to use vector components in order to solve those problems. So follow me on to the next lesson. We will get more practice with vector components and calculating those components in physics. Learn anything at mathandscience.com.